Welcome to Group Two's presentation where we have conducted a survey on security and reliability of IoT devices using blockchain and edge computing. This is presented by Giancarlos, Donna, Daniel, and Jose. Typically, IoT devices are deployed in open environments, meaning they are at risk for physical or remote attacks. As IoT becomes more pervasive and used in both the personal and corporate setting, a lot of the data has to be secured since it is sensitive information. Regarding reliability, if an IoT device is not secured, then it cannot be considered reliable because a lot of the data could be falsified or missing. Thus, our problem is that the traditional IoT model involving only the cloud is not secure and reliable. Issues such as high latency and poor bandwidth cause situations where quick responses are needed to be delayed and put the systems at risk. Another issue is that many times IoT devices have a low amount of physical resources since they tend to be so small. Due to the low amount of resources, IoT devices many times cannot run a reliable threat detection system nor encrypt data. Another issue is that most times an IoT device has limitations on getting updated. All of these issues can lead to poor reliability and mainly a lack of transparency on the data. The traditional IoT model is that the IoT device communicates with the cloud directly via the internet. The cloud handles all the major data processing required in order to display that information at the user interface. However, the problem with this model is that it is unreliable for edge users. Edge users are those that use the data retrieved from the IoT device nearby. Sending the data to the cloud and back to a nearby location is an issue for time-sensitive data. The cloud handles a lot of information from multiple sources, which leads to delays in the process data retrieval. The reason the IoT device itself cannot process this data is due to the limited physical resources. Thus, in that regard, the traditional model is not reliable for time-sensitive data. In terms of security, the cloud is very secure because it is usually in a centralized location. However, the IoT device is not secure at all in most cases. We have conducted a survey on various methods to improve the traditional IoT model. These methods are fog computing, blockchain, smart contracts, data storage and protection methods, and physical and clonable functions. We will cover the benefits and drawbacks of each of these topics individually, and then we will explore how they can all be used in conjunction to form the ideal IoT setup. We will begin by introducing fog computing. It is basically bringing computing power to the edge of the IoT device, that way the data processing can be handled locally. This eliminates the majority of the bandwidth and latency issues that occur when relying solely on the cloud. The cloud is still used in conjunction with the fog for more demanding tasks since the fog node itself is not super powerful, but it is much more powerful than the IoT device. We can observe in the table below the difference between cloud computing and fog computing. The major difference is the response time and the bandwidth usage. However, with these benefits comes the added risk of security issues due to the decentralized nature of fog nodes. In these images, we can observe a fog computing setup. The fog node serves as the middleman between the IoT device and the cloud. In the edge user case for time-sensitive data, if the fog node is capable of handling the data, it will output that data directly to the edge device. However, if the use case is more remote and not time sensitive, then the fog node will transmit that data to the cloud and the cloud will process it. The user can then access the data from the cloud at their leisure. As we can observe on the left, fog nodes are able to communicate with other fog nodes, and they can use this communication to pool resources or store data locally for a short period of time. The table below demonstrates the different attacks and security threats that can occur at each level of the setup. As we can observe, the most at risk are the IoT device and the fog nodes given their decentralized nature. The distributed and open structure of fog computing is vulnerable in many ways, such as unguarded nodes can be easily destroyed or tampered with physically to send false data. Man-in-the-middle attacks are possible as demonstrated in the image below, where someone is in the middle between the fog node and the cloud. The fog and the cloud believe to be interacting with each other, but in reality it is interacting through a third party. This third party could eavesdrop or alter the data shared maliciously. Other issues are lack of authentication methods, which can result in spoofed or hijacked nodes to be passed off as a reliable valid node, A denial of service attack can occur as well when a malicious user floods the system with too many requests, causing it to no longer work. And there are several more issues with fog computing regarding security concerns. Fog computing can improve the reliability of the IoT applications, but they cannot provide strong security on their own. Thus, if they are not secure, they are not truly reliable. Fog computing compromises identity privacy, which are the attributes that define the identity of the users, such as username, passwords, phone number, addresses, etc. This could be exposed through a hacked fog node. Data privacy is another concern where sensitive data could be collected from an unauthorized user through eavesdropping, as these images show. Another issue is usage privacy. Usage patterns can be collected by a malicious user to identify habits of the IoT system. For example, an attacker could identify the time an authorized user is not home. And finally, there's an issue with location privacy. Mobile IoT and fog nodes could be tracked by a malicious user to determine routing and more of the system.
One of the solutions to the data security issue in fog computing is blockchain. Blockchain can be public, private, or consortium blockchain. Consortium blockchain, also known as federated blockchain, is when multiple organizations govern the platform. It is permissioned rather than public, and it offers decentralization, which means that every organization checks each other for illegal transactions. The main features of consortium blockchain include faster speed, scalability, low transaction costs, low energy consumption, no risk of 51% attacks, and no criminal activity. Blockchain platform can be permissionless or permissioned. An example of permissioned platform is private and consortium blockchain, while an example of permissionless platform is public blockchain. The benefits of using blockchain for data encryption include faster speed, scalability, low transaction costs, low energy consumption, no risk of 51% attacks, no criminal activity, and the presence of regulations, which all nodes on the network have to obey. There are, however, several drawbacks of using blockchain. The first one is private key leakage. It means that the elliptic curve digital signature algorithm, which is used to generate the private key of the user, can be vulnerable. Private key leakage allows for many types of attacks, such as key attack, replay attack, and impersonation attack. The second drawback is double spending. It means that the same bitcoins can be used more than once. This vulnerability can be exploited in the following cases. When a user sends the currency to two different addresses in a rapid succession, and when one transaction is pre-mined into a block and the user spends the same coins before releasing the block. Transaction privacy leakage is another drawback of using blockchain. Since private key needs to be assigned to each transaction, transaction privacy leakage can occur when privacy protection measures in blockchain are not efficient, especially considering the fact that almost 67% of all transactions do not contain private key encryption. 51% vulnerability takes place when a user has more than 50% of the total computing power of the entire blockchain. In that scenario, the user can tamper with information on the platform, reverse or exclude transactions, and hamper normal mining operations. Last two drawbacks of using blockchain include selfish and reputation-based behaviors, as well as increased risk of identity-based attacks and data manipulation-based attacks. Selfish and reputation-based behaviors include actions such as hiding blocks, whitewashing, and refusal to sign. Hiding blocks means that an agent only exposes transactions that have a positive impact on his reputation and hides the ones with negative reputation. Whitewashing means that an agent can get rid of its bad reputation by making a new identity, and refusal to sign means that a malicious agent can decide to not sign a transaction that is not in his favor. On this slide, we can see a blockchain-enabled fog computing IoT setup with 4 different layers: IoT device layer, blockchain edge layer, blockchain network layer, and the cloud computing layer. All the layers interact with each other through the means of ID management, spectrum management, network services, network access control, edge and cloud orchestration, and data caching and storage. A possible way to further enforce blockchain is through smart contracts. Smart contracts are scripts that reside on the blockchain and allow for the automation of multi-step processes. Smart contracts were introduced by Nick Szabo in 1994 and have been defined as computerized transaction protocol that executes the terms of a contract. The basic concept behind smart contracts is translating contractual clauses into code and embedding them into property, such as hardware and software, that can self-enforce them. Such solution minimizes the need for trusted intermediaries between transacting parties and minimizes the occurrence of malicious or accidental exceptions. Smart contracts are scripts stored on a blockchain, what can be analogous to stored procedures in a relational database management system. Each smart contract resides on a chain with unique address and is triggered by a transaction address to it. Smart contracts allow for general-purpose computations on the chain. They also give rise to decentralized autonomous organizations, which are entities on the blockchain whose behavior may be modified.
Since smart contracts are programs that are stored in a blockchain network and are executed when necessary conditions are met, this allows us to create decentralized applications for almost any type of implementation. Smart contracts, besides of being stored in a blockchain network, they also act as a separate identity in a blockchain network that is able to receive transactions to its address in order to trigger its functions. Smart contracts also allows us to express logic as code, just like most programming languages. And finally, all interactions with the smart contract get recorded on the blockchain network and can be traceable. It is possible to develop smart contracts that are able to support communication among two parties. In the context of IoT, smart contracts serve as the intermediary in which users are sending messages, and then the smart contract indexes and distributes the messages to the corresponding destinations. Since only authenticated users in a blockchain network can interact with the smart contracts, and this information is transmitted to the smart contract, it is possible to authenticate users to make sure that devices are controlled only by authorized users. One example of achieving this is illustrated on the image on the right, where using the Solidity smart programming language, a smart contract can be developed on the Ethereum blockchain network. The smart contract illustrated sets the owner to be the user who deployed the smart contract and uses this information to make sure to receive messages only from the deployer or owner of the smart contract. On the paper titled IoT Public Fog Nodes Repudiation System, a decentralized solution using Ethereum blockchain, the authors proposed the following system architecture. The author explained that it is needed for IoT clients to establish trust in fog nodes that are used for storage, computation, or communication with the decentralized data centers. In order to achieve this, the authors define that it is necessary to define an architecture that provides IoT clients the means to choose the best suitable available fog nodes. This architecture consists in the fog nodes to be evaluated, the IoT clients that evaluate the fog nodes, and the Ethereum smart contracts that are used to communicate and interact between the fog nodes and the IoT devices. Users or clients' devices are able to interact with the IoT devices through the use of the centralized app in order to interact with the blockchain smart contracts. Now, how can we further secure this IoT blockchain data on the servers? One way is to use user authentication with the blockchain and smart contracts. Another way to do this is through access key updates for IoT devices using attribute-based encryption and creating this set of keys with the help of PUFs. Also securing fog nodes used for computation, storage, or communication, and also using data protection models such as shared and spread data among different data centers.
Data model for traditional fog setup. First, let's talk about the offloading model. The offloading model is when data is generated from edge devices or offloaded to the nearest fog node with cloud access, and in the reverse order from the cloud to edge devices. And below there is a diagram that shows how the process is actually done. Now, our next data model for traditional fog setup is the aggregation model. Now, with the aggregation model, data streams generated by multiple edge devices are aggregated and possibly processed at the nearest fog node before being uploaded to the cloud data center. Fog nodes pool resources and complete capable tasks before resorting to the cloud. Now, below we have a photo that illustrates the aggregation model process. Typical data load of a fog system. Here we have displayed an illustrative design of how a data load of a fog system would typically flow. The amount of data per transaction going from the IoT networks, then we have the fog layer consisting of the gateways, then through and from the cloud and the IoT networks. Data management and protection. Now, given the nature of IoT devices, limited resources make it difficult to encrypt and or decrypt data that requires a high level of protection between the IoT node and the fog node. Thus, these traditional models put sensitive data at risk. Also, many times IoT manufacturers resort to lightweight encryption algorithms or masking techniques to make up for it. For a more secure and better data management and protection, we propose using a lightweight P2P model using blockchain technology to encrypt data retrieved from the IoT device to the fog node. Now, a P2P or a peer-to-peer model, it's fog nodes which are at the proximity of IoT devices share their computing and storage capabilities and cooperate in order to offer a storage and computing layer to edge users. These nodes validate the blockchain and use an algorithm to form a common agreement on data retrieved from the IoT devices. Developing region-based trust through blockchain. New nodes can be added to a region through the blockchain using the identity key of a fog node. An address can be generated and the new node can send a transaction through the existing blockchain. Using the peer-to-peer network, if a consensus is reached on the trustability of the new node, it will be added to the region. Now, the procedure can be broken down into 3 steps. So the first, The new region sends a request to the original region for establishing trust between them. Second, the original region analyzes the request whether it can or cannot establish the trust through a consensus protocol. Now, third and final, once the two regions accept the trust established, the trust relationship is updated on the blockchain of these regions. Region-based trust aware. Now, the region-based trust aware handles newly joined devices coming from other regions. Below, in this design, we can see a region could be structured by one or several fog nodes. A fog node consists of several fog devices with weak performances which are deployed at the edge network. It can provide computation, network resources, and storages. The fog devices are heterogeneous, ranging from high-end servers to end devices, such as mobile devices, wearable devices. Now, a region structure could be broken down like this. Region 1 by fog node 1 and fog node 2, while region 2 is formed by fog node 3 and fog node 4. Data protection model. Shred and spread method for protecting IoT device private keys digitally. Shred and spread models shreds files on the client side in fog and spreads them over multiple clouds. Metadata privacy control takes place in fog, while scalable storage remains in the cloud. Shown in our shred and spread illustrations, we can see how this data protection model really works. By shredding a file on the fog side and then spreading the bytes across multiple public clouds in the client shim layer of a given file across multiple cloud storage providers, it can be assured that privacy of the data is maintained even if encryption keys is leaked by any given cloud provider. Blockchain data management method for low storage devices. Fog nodes can delete old blocks and keep new blocks depending on the IoT device usage and purpose. Many times, IoT systems only require data from a short time frame. And an example, as short as 1 week.
We can add an extra layer of security to an IoT system by using a physical unclonable function. A PUF is basically the machine fingerprint of an IoT device. This is done by modifying physical factors on the integrated circuit during the IoT device's manufacturing process. When a certain input is provided, a physically defined digital fingerprint is outputted. PUFs are used to generate keys to confirm device identity. Once the key has been saved, they are destroyed immediately for security purposes. These keys can be stored on the blockchain using an attribute-based encryption layer to ensure data authenticity. Based on our survey on different solutions for IoT security and reliability, we propose combining the following topics to have an optimal IoT setup with safe and accurate data usage. Our solution would consist of the following: a fog layer to enhance reliability of IoT devices, PUFs to ensure authenticity of IoT and fog devices, a multi-layer consortium-style blockchain to ensure data transparency and restrict unauthorized access. This multi-layer consortium-style blockchain would consist of the following: an attribute-based encryption layer for PUFs and users, and an IoT data layer. We will also consider smart contracts and data storage protection models.
The attribute-based encryption chain is a consortium blockchain which stores ABE encrypted session keys. These session keys can be used for access control for IoT devices. In order to retrieve access keys from the attribute-based encryption, it is necessary for users to have the set of attributes that are associated with the access keys. The PUFs can be used for generating the unique identities and attributes for each IoT device, and these attributes can be used by users in order to retrieve their access keys and gain access to the IoT devices.
Traditional IoT models consist of a centralized data center, which is responsible for collecting and processing data from connected devices. Such model is not efficient nowadays with growing number of IoT devices and the increasing amount of data generated by them. In order to efficiently process and store vast amounts of security and safety critical data, we can implement various data solutions such as cloud computing and fog computing. In cloud computing, the quality of service might be affected by its deteriorated bandwidth and connectivity. Fog computing offers distributed and decentralized solutions to resolving the drawbacks of cloud-centric approach. Fog computing also enables security and analysis of the latency-sensitive data directly at the network's edge. An example of an IoT data chain is a multi-layer blockchain system. As we can see in the research by Wang and colleagues, IoT chain can be an arbitrary blockchain storing phish data encrypted with session keys. ABE chain, on the other hand, is a consortium blockchain that stores ABE encrypted session keys for access control. On the image, we can see that in the IoT chain, various data sources collect the phish supply chain data. Data is encrypted with a session key and then published to the IoT chain by embedding the encrypted data in transactions. The IoT chain can be any existing blockchain or self-built blockchain as long as the blockchain can store arbitrary data.
Finally, we propose the following model in order to secure and exchange data between users and IoT devices, where IoT devices use PUFs in order to generate keys that are stored in the IoT data chain and are encrypted using the attribute-based encryption. The smart contracts are used to authenticate users interacting with the IoT devices and obtain the corresponding key for interacting with the device through the fog node. Finally, the users are able to interact with the devices as long as they have the corresponding attributes and credentials for interacting and retrieving data from the IoT device.
These are the sources for the images we use throughout the presentation. These are the sources for the research we conducted.
Thank you for your time, and I hope you enjoyed the presentation.